So far we have talked about continuity. We've talked about a graph being continuous at certain values, and that's really important. Today we're going to change gears and we're going to talk about differentiability. Okay? It's a fancy word for can you find the derivative? In order for the derivative to exist, the left and right-hand derivatives at the point must be the same value. All right, so like continuity. Remember with continuity, the limit had to exist in order to be continuous. You had to approach the same thing from the left and the right-hand side. That's true with differentiability as well. The slopes have to be approaching the same value. Now, I don't love this definition because I think it needs one more step. And the equation, or the graph, I'll call it the graph. And the graph must be continuous. That is what a derivative is, and that's how we can decide if something is differentiable or not. There are 4 reasons why the derivative would not exist. Okay? Reason number 1 is this absolute value graph. What is true about the slope over here? What is the slope? The -1. F prime is of x is equal to -1 over here. What is true about the derivative over here? It's 1. That's very much the same the whole time. So what is the derivative at 0? There isn't one, is the correct answer. It's D and E. The 2 slopes must be equal to each other. Okay, they have to be approaching the same value. Here it's not. You cannot find the derivative at a corner point. If you have a corner point, it is not differentiable. And so like right there, this graph is differentiable everywhere but 0. But at 0, it's not differentiable because it's a corner point. Let's look at number 2. Number 2 has this graph, an x of 2/3 power, x to the 2/3. Over here, kind of harder to see, but your slope's getting really close to -2. Over here, your slope is really close to +2. What is the slope at 0? What is f prime at 0 going to be? It's D and E. Because those 2 things are not exactly the same, or not approaching the same number, it doesn't exist. This is called a cusp. A cusp is a fancy word for a corner point. You don't have to use it, but know what it is. It's when one of your 2 lines is curved, or maybe both. Okay, that's what a cusp is. You can just call it a corner point. Okay, it's the same thing. Vertical tangents. A vertical tangent, that is where the slope of the tangent is infinity. For example, zoom in right here. At this spot right there, what would you say is true about the slope? It's vertical, correct? If something is a vertical line, what is the slope of a vertical line? It's undefined. You can't find the slope. It's undefined. There is no value. And so the derivative, f prime of 0 for this graph, because it's a vertical tangent line, because it's going straight up and down, it's going to be D and E. That one's hard to see. I don't love that question in this case because it's kind of a judgment call. At times you're having to make a decision there. And then the last one, and probably the most important one, where the slope things don't matter. Like, I don't care that the slope's the same on the left and the right. On the left side of 0, what's the slope? 0. What's the slope on the right side of 0? They're both 0. But it is not differentiable. Okay? If it's not continuous, then game over. It is not differentiable. The answer to what is f prime at 0? F prime at 0 does not exist. If you go back to the example we did just a second ago, and you look at our graph, it's going to load eventually. There we go. At this corner point right there, the derivative did not exist, right? We had a limit. If you were looking at 2, what is the derivative at 2? There isn't one because there's 2 open circles. You don't have a derivative there. Okay, if I were to take the derivative of this graph for letter B at 2, it does not exist because there is no value. There's a discontinuity there. We can't make that graph. So if your graph is discontinuous, the derivative does not exist at that value. That's a really important concept. Out of everything we learned today, that's the most important thing. Down below, compare the left and the right-hand derivatives to show that the function is not differentiable at x equals 0. Graph this thing. Find the slope on the left and the right hand of 0. Here we go. We graphed that thing out on the left side of 0. Okay, there's no good way of writing this out like limits. But over here, as we get closer and closer to 0, what is my slope getting closer and closer to? It's 0. It's the top of a parabola, so I'm getting closer and closer to 0. On the right side of 0, what is the slope of that line going to be? 2. This guy over here, it's just a straight line. The slope is 2. What is f prime at 0 then? F prime of 0 is DNE. What kind of point is it right there at 0? That's a cusp. It's a cusp. It's a corner point. It's not smooth. So if it's not smooth, it doesn't exist. We're going to go through this next one pretty quickly. There's some good merit to it, but at the same time, it's kind of elementary at times too. We are graphing this thing right here. Show me with your arms. What's that shape look like? Point, which direction does the -2 take you? Point, which direction does the +3 take you? Graph it. At what point does the function appear to be differentiable? I'll start us off here. This thing is differentiable at all numbers, except x cannot be one number. Caitlin, what's the only value where x cannot be differentiable on this graph? Yeah, why is x not differentiable at 2? Yep, it's got a corner point at 2, and so it's not differentiable. That's an n, even though it doesn't look like it. At what point is the function continuous but not differentiable? Apparently it wanted me to flip sides. When is that graph continuous but not differentiable? Nick, what do you think? 2. At 2. We just said that information. X is equal to 2. It's continuous. How do you know it's continuous, Nick? Limit and value is the same. You didn't pick up your pencil. It's continuous. At what point is the function neither continuous nor differentiable? None. It's an absolute value graph. Absolute value graphs are continuous. It's a V shape. Kind of simple, but again, we're just trying to reinforce these ideas. This is the key to today's lesson. Out of everything we've done, this is the most important thing. Make sure you got it. Differentiability and continuity. A function that is differentiable at a point or over an interval will always be continuous. If you say that something is differentiable, it is implied and it is guaranteed that that thing is continuous. However, the converse is not true. If something is continuous, that does not mean it's differentiable. All right, that's super important. Let's visually see what's happening here. Okay, this next little thing, it helps me a lot, but maybe it doesn't help you. We'll see. I think it's beneficial. So think back to geometry class. Remember geometry class? Yeah. What shape is this? That's a square. It's a square. That square right there, is it a rectangle? Yes. If it's a square, if I say, hey, you've got a square, you can already tell me that it's also a rectangle. Okay? That's definitely how you spell rectangle. I'm going to draw a rectangle right now. Okay? I'm going to draw a rectangle. Is it a square? You don't know is the right answer. Here's my rectangle. Is it a square? Yeah, it's a square. It's a square. Here's my rectangle. Is that a square? No. You get the idea. I'm going to draw something that is not a rectangle. Is it a square? No. If I draw a triangle, is that a square? No, you can't do it. So here's what that means. If I tell you I'm going to draw a square, you know that that square is a square and a rectangle. That's guaranteed. If I tell you I'm drawing something that is not a rectangle, you know that it's not a rectangle and also that it's not a square. If I draw a rectangle, you say, it could be a square. I don't know. Everybody agree with me on that? For that thing, a square is like differentiable. If I am telling you something is differentiable, if it is a square, it is guaranteed that it is continuous. If you're a square, you're automatically a rectangle. If you're differentiable, you're automatically continuous. If I tell you something is not continuous, is it differentiable? No, it's guaranteed. If it's not continuous, you can't be differentiable. If I tell you something is continuous, you don't know what it is. It could be differentiable, but it doesn't have to be. Kind of makes sense. It makes sense to me. So I don't care if it doesn't make sense to you. It works for me. So we're going to deal with it. All right, so let's go down to the bottom of these notes. Here we go. At what domain values does this function appear to be differentiable? Show me with your fingers how many places on that graph is that thing not differentiable. Pon, in what 3 places do you think that this thing is not differentiable? 0 and 2. So -3, 0, and 2. That's when x is not. So where does it appear to be differentiable? All real numbers but that. When does it appear to be continuous but not differentiable? Katie, when is that graph continuous but not differentiable? So we helped us out here because Ponin listed when it was not differentiable, right? -3, 0, and 2. So basically you just got to look at those 3 points because you want to know when it's not differentiable. -3 and 0. Why is it continuous but not differentiable at -3 and 0? You don't have to pick up your pencil, but it's a corner point. Good. So -3 and 0, it's continuous but not differentiable. When is it neither continuous nor differentiable, Maya? Yep. And why is it not differentiable? There you go. Yep. It's not differentiable because it's not continuous. And so they didn't even have to put this part. If they just said not continuous, then it's 2. And that's the end of the story. Everybody okay with that? Down below it says, let f be a function with f prime of 5 is equal to 8. Which of the following statements must be true? Talk those over with your neighbor. Get me an answer. I'm seeing lots of 2s. Let's check. F prime of 5 is equal to 8. Or in other words, is that thing differentiable at 5? Yes, it is differentiable because it's telling you what the derivative is. It's differentiable. So if I'm telling you something is differentiable, is it continuous? Yeah, done. If you're differentiable, it's guaranteed that it's continuous. We know that for a fact. Go to the next one. Look at example 5. Same idea. Get me an answer. Show me with your fingers. F is continuous at x equals -11. What's that tell you? A, B, C. If it's continuous, is it differentiable? Not necessarily. It might be. Is it not differentiable? Not necessarily. And so think about this. Is this graph right here continuous? Yeah, cool. Then I can find the derivative right there. Is this graph continuous? Yeah, but I can't find the derivative right there. That's 2 different options. I don't know which one it is, so there's not enough information to make that decision right now. Looking at that graph, go through those really quickly. Fairman, at what x values is that function discontinuous? -1, 0, and 1. Okay, good. Isaiah, at which values is that function not differentiable?
-1, 0, 1, and
Why could you include negative 1, 0, and 1? If they're not continuous, it's guaranteed that they're not differentiable. And then why did you include 2? Corner. At 2, it's a corner point. So cool, done. At what x values is the thing continuous but not differentiable? Obviously 2. It's the one that's left out. Everybody good with those concepts? All right. This last part of the lesson will take me 2 minutes to go over, and that's all I need. Okay? Break out your graphing calculators really quickly. So we did this bell work the other day. Remember doing this? I think we did it Friday. We found the limit as h approaches 0 of negative 2x squared plus 3x plus 9 at x equals 1. What is that doing when we found that limit? It found the derivative. It found the slope at 1. Everybody agree with me? Remember how fun this was? Oh, yeah. All that work to get an answer of negative 1. Our calculator will do that. Now, I will say that our calculator is not the smartest thing in the world when we get to derivatives, so you have to be careful when we do it, and we'll talk about that later. But pull out your graphing calculator. We're going to use this example from notes the other day because we know what the answer is. We know the answer is negative 1. And so we are going to find the derivative, numerical derivative of that thing at 1. So in my calculator, I'm going to hit the math button, and I'm going to hit math 8 because math 8 is right here for n derive, okay, or the numerical derivative, or the derivative at a number. Okay, so we're going to go to number 8. We're going to hit enter. I've updated everyone's calculator. I did that at the very beginning of the year. You've forgotten already, but I did that. Yeah. So everyone should look like this. Does everybody's screen looks like this? Okay, cool. Right there, it's d over d something. What do you think goes with that d down below? We did that yesterday. It's x. It's d over dx. That stands for the derivative. Okay, we're taking the derivative with respect to x. And so that's what we're typing in there. Inside the parentheses, that's going to be the equation. So we are going to take the numerical derivative of this thing. So negative 2x squared plus 3x plus 9. So in the parentheses right there, I'm going to type in negative 2x squared plus 3x plus 9. Then you got to hit the over button and get down into this last box where it says x equals blank. And in that box right there, you're going to type in whatever number you want. We're going to find the derivative at 1. And so if I type that in, I hit enter, it will get me the numerical derivative that I wanted. The answer that we were looking for was negative 1. We typed it in, we hit enter, it gave us that answer. Make sense?
Like, why do you have to do, like, why is there an option for, like, d over d?
You know what? I haven't gotten into that very much. I know that later on we will find derivatives with other things besides x. Like we can find the derivatives with time and other parts. Not confident. I've never done a problem that's not dx on the bottom. All right. So in your notes, you're doing this problem right here. You're finding the numerical derivative of e to the x plus x squared plus 1. Is that right? And what are you finding the derivative at x equals what? Do that. So this is f of x. Our job is to find f prime at 3. And so to find f prime at 3, we are using our calculator. We are going math 8 dx on bottom. Inside the equation, we're going e to the x plus x squared plus 1. And at the end, it's x equals whatever my x value is. In this case, it's 3. I hit enter. I get an answer. Is that what you got? 26.08. How many decimals? 3. It's calculus. We always go to 3 decimals every single time unless they specifically state not to. 26.086 is the correct answer for this. Then it'll be completely wrong. You have to go 3 decimals. So there is no thought process. It's always 3 decimals. Questions here?